the Indian Association of Structural Engineers, known as IS-Struct-E, was conceptualized and constituted in the year 2002 by a group of senior professional structural engineers from all over the country. IS-Struct-E is registered under the Societies Registration Act 21 of 1860. IS-Struct-E is a national apex body of structural engineers in India with a mission to promote structural engineering profession and cater to the professional needs of the structural fraternity. In the short span of 2 decades, association has attained an eminent position in the professional field. Its membership is valued very highly in the profession. Since inception, IS-Struct-E has been led by eminent structural engineers like late Shri Mahendra Raj, late Shri Shri Kumar Ghosh, Shri Subhash Chand Mehrotra, Professor Mahendran, Shri Alok Bhaumik, Shri Manoj Mittal and Professor R. Pradeep Kumar. As its president, IS-Struct-E is a permanent member of Engineering Council of India and interacts with the government on professional and policy matters related to civil and structural engineers. To expand its reach, IS-Struct-E has collaboration with various international professional like-minded associations and institutions. IS-Struct-E's prime objective is supporting and protecting the profession of structural engineering by upholding professional standards and acting as a mouthpiece for structural engineers in India. IS-Struct-E endeavor to ensure that its members develop the necessary skill in structural engineering and work to the highest standards by maintaining a commitment to professional ethics and standards. IS-Struct-E is actively engaged in organizing several continuing professional development (CPD) courses for structural engineers to help them update their knowledge and advance their career paths. It also conducts refresher courses for young and practicing engineers and student-oriented programs. Seminars, workshops, conferences, technical lectures and discussions related to the latest technological advancements and case studies are also organized regularly for members to enable them to continuously update their knowledge and skill set by interacting with the best minds from the industry. IS-Struct-E's activities are widely appreciated and known for quality technical contents. IS-Struct-E is also actively engaged in publishing its quarterly journal Structural Engineering Digest (SED), code commentaries, professional guidelines, and a monthly newsletter. IS-Struct-E's publications are becoming popular with time. IS-Struct-E has representation in various technical committees of BIS and IRC as well. Its members are actively contributing to National Code of Formulations. In the year 2020, IS-Struct-E started National Awards competition to stimulate interest in the structural engineering field and to promote innovative thinking and creativity. The awards are presented to the winners in recognition of their outstanding contribution to structural engineering in the categories which include Outstanding Structure, Outstanding Structural Engineer, Outstanding Woman Structural Engineer, Promising Young Structural Engineer, and Best Master's Thesis in Structural Engineering. IS-Struct-E is currently operating from 4 regional centers, namely Eastern, Western, Northern, and Southern, having its headquarters in Delhi to inculcate the professional culture and provide handholding to the budding engineers. IS-Struct-E has its student chapters in several leading engineering institutions as well. Membership of IS-Struct-E is open to all civil and structural engineers engaged in structural engineering profession. Members are elected based on their qualifications and experience in different grades as per eligibility requirements prescribed in the bylaws. Each application is carefully scrutinized before electing the members. More information about IS-Struct-E is available on its website www.isstruct-e.co.in.
Vikas?
Yes, sir. Yes, sir. Please start, sir.
Shall I proceed?
Yes, sir.
Dear friends, welcome to the webinar. Today's topic is major durability concrete for concrete structures in India. Focus would be on corrosion issues and way forward. The speaker is Dr. Vishwajit Bhattacharjee, an emeritus professor from IIT Delhi. He is an esteemed expert in the field of civil engineering with significant contribution to concrete technology, durability, and sustainability. He graduated from IIT Kharagpur way back in 1978, worked in the industry with Cummins in the construction of important bridge for 2 years, and later on pursued his further studies, did his MTech and PhD from IIT Delhi, and thereafter he has been teaching and doing research in the IIT Delhi. He has extensive experience in research, consultancy, and industry training with over 250 consultancy projects, and he has published over 180 published papers. His expertise spans concrete porosity, rebar corrosion, energy efficient buildings, sustainable buildings, and many more topics. Now, brief about the topic is the presentation will address various types of cracks in concrete structures with the focus on rebar corrosion as a critical durability concern. Drawing from his 35 years of consultancy experience, Professor Bhattacharjee will illustrate the causes, implication, and solution related to corrosion, including its impact on life cycle costs, carbon emissions, and sustainability. The session would highlight service life design, preventive strategy, and the need for India-specific research in concrete durability. Now, I request Professor Bhattacharjee to proceed. Professor Bhattacharjee, please proceed.
Yes. Thank you, Dr. Dhawan. It's been a pleasure that you requested me, and it's a pleasure to talk talk in a forum of iStruct. I'm grateful to iStruct and you in particular, because earlier also I had a lecture long back.
Yes.
And thank you very much. So if anyone wants to interact in between also is possible.
No, we'll listen to you and thereafter we'll.
Sure. Okay then. So I can share my slides, screen and slides. Share full screen. Where is it? Screen, yes. Share. That's right. And if I go to the slideshow from beginning, yes, that's what it is. So is it visible to everybody, slideshow?
Yes.
Yes, sir. Yes, sir.
Okay, so that's what it is. Well, I think the outline I am not going, because I'd like to already, Dr. Dhawan has highlighted the outline. So I'm straight away onto the issue. Now, I think one must distinguish between defects and distress in concrete. Defect comes usually early, and they include what is called intrinsic cracks, like shrinkage cracks, thermal cracks, And even early cracks can come from contamination that I have come across one of them. So I'll be highlighting those ones which I have come across, the early defects. This diagram is available in many books, including Neville and Brooks, Mungie and Millard, and so on. And it tells you the types of cracks that you come across in concrete generally. For example, ABC is a mouse visible. ABC, these are actually ABC, plastic settlement crack, right? So I suppose this ABC are plastic settlement cracks. Then DEF are early shrinkage cracks. E is here. E is here. That's normally on flat surface pavement. They get it quite often. And D is somewhere there. Sometime in thin sections, you get shrinkage cracks, through and through even. For example, I could be one of them. GH is thermal. So these are on thick sections. Normally you get thermal cracks. And I is drying shrinkage. 5-6 months can occur. I'll have some examples. That's what we are doing. Crazing doesn't create much of a problem. It gives an ugly look. J and K, very fine cracks, do not penetrate much. And this one is a rebar corrosion, L. Right? Structural cracks are, of course, where the flexural moment will be maximum, or shear and things like that. It comes from there. Alkali aggregate reaction is something of this kind. So this is how people have actually, highlighted the nature of the cracks as can be seen visually. Now, I'm just going to go across some of the cracks that I have come across over the years. Long wall without construction joint in a water tank, M20 grade of concrete. And you can see the section thickness is 115 mm at the top and bottom 250 millimeter. Sorry, long wall without construction joint again, because water tank, so basement, they were keeping it like that. And this was a very peculiar case of a factory building. Previous one was a factory building. This was for water tank and manual curing and so on and so forth. So vertical cracks, I'll show them actually. Then shrinkage cracks in precast rings for tunnel lining. M45 grade of concrete, curing was inappropriate. They used curing compound, which is not suitable for Indian tropical climate. Obviously, because you can understand the consultant was a foreign consultant, even the engineer was a foreign engineer, after which an Indian engineer took up, and then he called me, and then the problem was sorted out. Multiple parallel cracks. I'll show them photographs of those ones. Then precast linear element, folded plate of factory building, thin again, steam cured, they got cracks. So they're all shrinkage cracks. Then precast plate elements for wall panels of factory building, again, shrinkage cracks. And precast double T-beam slab elements for railway track system, M55 grade of concrete. Again, it's a, slab portion crack, shrinkage of slab portion resulting in cracks in beam portion, as which I shall see. And again, you have a foreign consultant here, European consultant, I suppose, who have no idea, and they were not even agreeing that this is shrinkage. I had to calculate. Obviously, I would have calculated. Do also FEM analysis to one of my students to show that the stresses from shrinkage can come somewhere at maximum. They would like to put it that to loading condition during, handling and all that. But reality, people who do not have idea about this climate of this country, they do bad job. So we should not depend all the time on foreign consultant. This is my, experience. Surface cracks developed in warehouse. That's because of thermal gradient. I'll show you. And vertical cracks in piers, heat of hydration cracks. I've seen more than one, but this is the one where I was involved in recent time. And, I shall show you through some sketches or photographs. Then chimneys. I think this is, cast in situ piles. This also I've seen more than one. But I'll highlight one case only. Because in cast in situ piles, what they do is they make the borehole to stabilize the surrounding soil. They put in bentonite slurry, and this bentonite actually stabilizes the soil by going into the pores of the soil system. Then the remaining bentonite has to be diluted to nearly one specific gravity. I mean, 100, 103 or whatever the specification is, density. And if this is not done properly, sufficient bentonite will stick there. So you pour in concrete through trimming, underwater concreting, and the concrete goes down below, the bentonite comes up from the top. Underwater concreting is used elsewhere also. I not exactly a witness, but the site where I worked in 79 or so, we had to do trimming concreting somewhere. Anyway, so coming back to this, but coal grouting, the bottom plug and top plug of well, that's also done almost in a similar manner, underwater concreting, but that's not trimming. So here what happened is bentonite contaminated the surface concrete because it was not diluted sufficiently. And for good reasons, the river decided to move away from it and it dried off and bentonite shrunk, causing concrete to crack. I'll show you that anyway. Honeycombed and defective concrete in chimney lift. I have seen number of them actually. Slip form construction. And if they have not synchronized with the setting, it was late. The slipping was relatively late and it took a chunk of concrete along with it. Although they don't use, you can't use a shuttering oil there. They use kind of a polished, formor. Because every time you can't apply the shuttering oil, there's some problem apparently. At least those places they were not doing, and it came out with it. So I have photograph of this also. Bar location of wrecker column in a cooling tower that got dislocated. Very interesting problem. And then other L is a removal of cover concrete and cracks 8 months old unloaded column. There was no load. It was not even finishings were not put in, but corners cracked, even rebar were exposed. And obviously people were not ready to accept that this could be due to some chemical reasons. They said, no, load the cement, come cement dala. Something like that, the strength anyway. So it was actually a chemical reason, which I had to prove, but to find some or other, my, people around were not very happy. Many cases of honeycombing and bug cases that I'm not discussing. So only some I am doing. It's not exhaustive in any case, as I said. So ABE type of cracks, shrinkage cracks in thin walls, they look like this. If there are buttresses, they will be between the buttress because it will try to shrink. And shrinkage can be calculated using ACI formula. And you can see that shrinkage occurs, the strength develops, tensile strength of concrete develops gradually. And when shrinkage stress is higher than the strength, cracks actually would come. So this can be done. This is for the case C, which was the tunnel lining ring, and you can see blue marks there. These are the cracks. These are the cracks. We actually mark them, red, blue, etc., depending upon thickness. I'm not going to go into the details of this. This was thin. And what happened is they use a curing compound, which is wax-based. Now, such wax-based curing compound in India in the month of May and June exposed concrete, it will simply melt. And the curing was not there. That is the reason, because drying shrinkage occurs because of poor curing often. It's there in that formula, SA formula also, which is available in my lecture of NPTEL lecture. I think it is module 7 or something, and also there in Neville and Brooks' book. This is more. We put some telltale one. Red one is a very thick crack, white crack. Then this is the case of that I was saying that precast slab and beam, T-beam system. The cracks as shown were here. This has been lifted like this. The cracked beams were cracked, and we could show that the cracking could occur, cracking at certain spaces that could occur, and not because of structural loading, as was pointed out by some of the people, especially the designer from abroad, because they could never view this, or they actually suggested also handling method and all. But the Indian environmental condition is not same as even in Mediterranean. The person who did the curing compound application in that ring, tunnel lining ring, was saying that, okay, we have done it in Mediterranean. But Delhi is different than Mediterranean climate. Dry climate, hot, dry desert climate. So this is important. This is a case of a container depot, Trimix concrete, that is a vacuum dried concrete. As you can see, reinforcement up there, and the cracks were seen right at the top. So thermal cycle of temperature gradient, this was exposed because they did not put the shed. And the cracks came because the temperature outside was high and solar radiation was falling directly onto it. Now the bottom, the plain concrete, PCC, would, is quite thick. It would restrain any kind of expansion or contraction of the thermal contraction and expansion of the top concrete. So when it was daytime, it was trying to expand. Possibly the expansion was resisted. So compression was there in the daytime, night. And it would go to say 35, 40 or 40 plus 35, 37 plus another 10, 12 degree centigrade because of solar radiation falling onto it. But then this heat would not actually penetrate into the PCC because there's a thickness of concrete there and there's a time lag. It will actually penetrate in the night, right? There's a phase lag, as we call it, 24-hourly cycle of thermal cycle. So it will reach in the PCC much later and it will be relatively at expanded state. But by the time early in the morning, the concrete would crack. Concrete would try to shrink, top Trimix concrete would try to shrink, but it will not be allowed to by the bottom system. And it caused crack parallel to the groove that they have cut in. They did not cover it. Next time onwards, they did cover, of course. This is for a heat of hydration scenario. And the cracks were somewhere, you can see the elevation of the pier, thick pier, 2.5 meter thick pier, 2.5 meter here in plan. And lift height were 2 meter initially, although later on by calculation or otherwise, not a very rigorous calculation. And the cracks were coming somewhere there. This is the elevation in between because of surface cracks only. They're not penetrating through and through, rarely penetrating through and through because surface was cooled down. Heat of hydration core did not, 2.5 meters, so inside core did not, and that resulted in cracking. What is typical thermal cracking this was. They use, of course, PPC. This is that pile case, dried bentonite shrinkage. This is the pile cap and the piles below. General view. And this is the cracks which were there in the pile. Individual piles, which are shown here, 4 or 5 piles, set of piles, and cracks were here. And then, in fact, in some places, river was simply out because the bentonite shrunk. Originally, it was underwater. After some time, it came into the dried scenario. Normally, they put well foundation in river, Indian big, wide rivers, Ganges, Brahmaputra, and perhaps not much of an Indus because in India, Indus in Ladakh, Leh is not that wide. But if you look at many of our rivers, they are very wide and quite deep at points, and they use well foundation. This was pile foundation, originally away from the waterways, but then river decided to change its course, and obviously it became dry, it became wet area. And next time again, the river went back when it dried, so it shrunk. So initially it swelled and then shrunk, and that resulted in that cracking. And this is a phenomenon I've seen at least in 2 places. This was the case where I was involved to diagnose. Other place was close to Allahabad. I have not tell about the, who are the organization and all that, because I think that's not ethical. They must have taken care of that. That's not nothing to be worried about them. Early defects coming from unsynchronized slip from operation. The concrete simply crumbled and went up because slip form was operated much later than setting or scheduled synchronized time. And this is the kind of concrete that you see. And I have seen, again, come across similar situations, seen once or twice, but reported number of times. This is one thing, they have to synchronize it properly. If you don't do that, it might result in this. So this you have to investigate the rest of the concrete, and if they're fine, you can repair this portion. This is that case of a Recker column, which is an inclined column used in for hyperabolic cooling tower. I think that's what it is. Shape-wise hyperabolic cooling tower. and inclined. And the reinforcement was, this is the original reinforcement cage. Not only it was small, its diameter was much less, it got shifted to one direction, and obviously the cover was very high. So it didn't serve the purpose. What I did was I said that, okay, you drill hole here, cut hole rather groups, and put epoxy of the similar strength of the concrete, because substrate and the concrete must have same, and put in the rebar of the same diameter, same type as much as possible. But then you have to confine it. So I use FRP wrapping to confine it for that portion, for that whole column, in fact. And I did calculate this using ACI methods. It's available in books, also Park and Pauling and things like that, which I studied in my BTech and similar sort of time, because I'm not a regular structural designer, but RC design, Professor Nair has taught me well, I can do that. That's not a problem. So understanding that. This is the case of a early distress pattern in a column where it simply spoiled off in 7-8 months time, no load, not even finishing load, right? And there were cracks. So I was puzzled that how can this happen? The bars were absolutely intact, and the loading would have caused, and it's a short column, not long column. Buckling is not possible. There are cracks here also. If this is fixed end, then this is the portion from, where the relatively the point of contraflexion, that's what it's called. So where there can be, so stress could be there. So what I guessed was that perhaps something like this is happening, some internal pressure, looking at the whole thing, the zone of stresses, the concrete spalled off here, as if there's some pressure inside. And this can only come from expansion. And my suspect was that there is some sort of sulfate in the system. Might have come from anywhere. Obviously, it was not easy to convince the structural designer think everything is under load and nothing else. Sorry, you are all structural engineers, but please, everything is not under the load. There are other problems in concrete too. Most of these cracks I am showing has hardly anything to the load. So internal sulfate, that's what it was. I had to prove it. So I asked for X-ray diffraction. Now this is the normal concrete X-ray diffraction, which doesn't have ettringite. Ettringite is the product from sulfate reaction, right? Ettringite quickly forms, but their surfaces are broken down because we had a little bit of gypsum in the cement system. But this had sufficient ones. The peaks at 27 represents ettringite, which was not there in normal concrete, as you can see in the left-hand bar. And then I took some more detail. I mean, they supplied me, I asked them to give me the X-ray diffraction diagram. They said, who understand this? Well, I said, I do. And it was ettringite was very much there. So my speculation, or rather my suspicion was correct. But where from it came, nobody knew. I mean, we didn't investigate further. So these are some cases of early defect. This is another case, a case of a cold joint in a Mevans shuttering, right? And then I had to identify that the concrete of the, cold joint, where the cold joint is there, here, because again, they delayed the lifting of the form wall. Mevans shuttering is everything together. So there's some sort of mismatch. And since it's set and then you poured in concrete, cold joint formation occurred. One has to prove so that this is happened. So I decided to go through ultrasonic pulse velocity test, which normally is my coursework. I do this diagram is there. And then red one shows the in case of poor layer, and that's what we find. So we measured in good places. Like as you can see, there are no, left-hand side. There are good places at certain spacing. We took ultrasonic pulse velocity, right, in one surface only, indirect. And this bent shows that sudden increase in velocity, because this is travel distance, this is time. So 1 over travel distance by time is a velocity. So velocity reduced suddenly, and that shows that there was a problem. So we anyway suggested repair scheme. I am not worried. Now comes to the point of durability. This is one case I came across in Northeast. Alkali aggregate reaction. It's again, and the base of a tower, base of a steel structure base, and this is the kind of cracks. Some structural engineering colleague of mine, sometime he just asked them, this is, must have been a load failure, and therefore you just do something, redo it and redo it. Not redo it, epoxy or something was suggested. But this was very much there, it didn't go away. And you can see that map cracking I show, M-type, this is what was available in the surrounding structures as well. Alkali aggregate reaction was my suspect. So I took some samples and looked in a microscope petrographically. My geology colleague in the lab, technical person, I gave him that, please find out is there is alkali silica gel, and he says yes, it is there, the white color alkali silica gel. So this is one case, Northeast, because they were using aggregates. Initially they tested for petrography, later it finished, and then they started using whatever is available. Normally, the aggregates which are already been used for many years, proven that there is no alkali aggregate reaction, like the one we use in Delhi or any other parts of the country, they are not prone to alkali aggregate reaction. So opal quartz, etc., whatever there. So these are the durability related. This is one durability related problem. I came, another was sulfate, which is not exactly durability. So if you see them, about 8, 10, and maybe another 5, 7 would be there, were early cracks. And this is a kind of durability crack I came. But then, this is what was most of the time I was asked to investigate, suggest a repair. Buildings, most. And some I compiled long back in 2005 or 6, published in ASC India Section Journal, because I thought it was for the people in the country, it's a good idea to put that experience for them. And the types of construction is given, pH of the concrete was measured, ratio of carbonation to cover depth. Some places we measured, some places, I mean, it would depend upon what the client want also. And you can have approximate ages also. This I would have shown in one of our ICI presentation. And the chloride, water-soluble chlorides, most of them show red because they were relatively high. Some cases pH was low. This is also 8.4 is also low. And this was definitely low. Now, generally what happens is where the life was longer, as you shall see, possibly in the bank office, this value was there. But since there was no moisture, there was no problem. But some good bank building, there were no problem at all, 50 years old. These are not exhaustive, there are many more. So 22 cases I am just showing, residential, telephone exchange, college hostel, and so on. Many of them did not have high chloride, but pH was problem. And some showed 20 years, but not 4 or 5 years, right? 20 years, but not 4 or 5 years. But if I go back, one of them would be showing 4 or 5 years. One of them would be showing 5 years of life. That is the first one, this one, and it had actually quite a bit of chloride in it. So that's one it is. Basically, this is one can use for diagnosis based on Bunge's book, but I suppose there may be changes in this because chloride business has been changing all over the world. Very much, if I look at we looked at the code 2007-8. After that, I have not really looked into changes in the code, but we found the chloride, threshold chloride level, as we call it, or permissible chloride level kept on changing from time to time, right? It started increasing. It became restrictive and more restrictive, stringent and stringent. So carbonation to cover depth more than 1, you have moderate risk of corrosion. But if it is also chloride, above 0.4, chloride content by mass of cement, 0.4, then it can be high. And alone, they say just threshold, maybe moderate, and high. But then we also translated it to pH, because this was carbonation to cover, somewhere around 8 or so. So you can say that similar sort of thing happens. Now this 0.4, chloride by mass of cement, Bunge suggests that you can take it to equivalent water-soluble chloride in this manner. Bunge, or there is another book, I'm not sure, 0.4% acid-soluble chloride, because that includes chloride that is bound chemically I mean, physically also part of it. So 0.4 divided by 7.5, because cement content it was. So around 1:, cement is to total concrete. They took it as 7.5. And chloride, total chloride to free chloride, total chloride divided by free chloride, water soluble chloride, total chloride is around 1.55 times. So 0.34 water soluble chloride, and equivalent could be thought of, but by mass of concrete is what we'll measure. Inside, in an existing structure, you can measure only by mass of concrete. Otherwise, there is a lot of error. Although a lot of people are reporting it in terms of cement or per meter cube, with IS 456-2000. Actually, IS 456-2000 restriction, which has come from BS code actually, or BS-EN now would be, but it has come actually from BS code. That was meant for fresh concrete, new concrete. Now, new concrete, every individual component, you know what is the total chloride. And you know the mass per unit volume of concrete, 300 kg per meter cube. Therefore, this is with respect to per meter cube. I think this adds in error. One should measure in situ. If one is measuring in concrete, then it should be per unit mass of concrete. And both total and water soluble is good. But water soluble is the one which contributes to corrosion. So 0.25 by mass of chloride, some literature, some even goes to 0.015. Right. So what we did was we looked into, we found 72% was showing chloride as the problem. Only 31% was showing carbonation. And if I combine carbonation and chloride, then there's an overlap. 16 plus 7 carbonation was there in, so I think, yeah, something of that kind. And then I just thought to fit a multiple regression data, and the time at which they came to us for repair, I call it time of repair, and it shows that ultrasonic pulse velocity, the strength, cover depth, etc., etc. Not a very good correlation, I'd say, but still it's okay, 84%. But this says the sound concrete tendency is better. Sound high ultrasonic pulse velocity became much later, which means the quality control was better. Most of the cements were, not most, all were OPC cement, mild steel, CTD, and TMT bars were also used. Some case, 5 years case used TMT and CTD in conjunction, because stirrups were not, of CTD was not available at that point. And so they corroded through galvanic corrosion. 2006 onwards, I came across a number of them, but I could quickly record some of them. And as you can see, some plant building was there. Chemical plant building and high polymer. I mean, polymer, they are producing. And there also we find that chloride was high. In 1970 and some in 86, some buildings, they were there. Came from the process, essentially, looks like. Then there's a water tank where we found again pH was quite relatively lower, and carbonation to cover depth was higher. The point that I'm making, water tank means moisture condition is conducive for carbonation as well. And chloride was relatively, there are some cases high chloride was not much really. Residential, 48 years, I think there were no, chloride was pretty less, but carbonation to cover depth was high. And another residential 8-story building, you have the ratio to carbonation depth was also fairly high, chloride was also high. And they came after, 15 years. That was not all that bad, I'll say. Construction 1995-96. Yeah, the first one, plant building, was obviously using chloride. It was a kind of metal, rare metal factory around. Now few specific cases. Water treatment plant. Beyond this, these are between 2006, beyond 2006, right? Some more I've just specifically put them. This is a water treatment plant which uses polyaluminum chloride. And that was a culprit. It actually spoiled everything, right? There's chloride all over the environment, and you have corrosion. This is somewhere external, even internal was their problem, where they were storing those. But the age was not all that bad. I think this was 10, 15 years or, that kind. Some 7, 8 years, 5 years, I said 7, 8 years corrosion. I deliberately kept them. Because where you have chemicals, you better be careful. If it is chloride, chemicals with chloride, for example, polyaluminum chloride and all that, it's not a organic compound, but still there's a poly involved. So they call it PAC. So used in water treatment and all that, chloride treatment of water. So this is 7, 8 years, right? I just searched in the reports of that locality whether there's water. The water had a lot of chloride or no, but it was not. And we measured all this, free chloride, relative moisture, etc., etc. And interestingly, this diagram I'm showing is a kind of it is a 35-story building, not one, several of them I picked up from one. And you have, chloride content as you go from bottom. 7th story, 6th story had pretty high chloride. And then again, 33rd story had quite high chloride. So it was there all through the heights, right? And then if I see the class interval of this chloride for many of the structures there, many towers of that area, number of them had high chloride. And mean, etc., given, the class interval is given. So the red line shows the threshold level. They did actually refurbishment work, right? They did. So they did refurbishment work. Okay, I think I'll go there first. Already they repaired it when I was called. And the area repaired was also known to us. And cost of repair was also known, right? In square meter, how much they have done. And, in basement, tower, etc., various towers and so on and so forth. And then I decided to plot probability of depassivation due to chloride, because probability of depassivation, I could find out how many samples taken from that particular case and how many of them are above 0.025. If I've taken 31, 1 is above, so probability of finding depassivation is 0.03, 1 divided by 31. And somewhere 0 because there are none found, a particular building. And then there were, somewhere out of 34, 24 had chloride higher than 0.025. So probability of depassivation I found 24 divided by 34, because that's how I had to analyze. And then I plotted this probability of depassivation versus, repaired area in square meter. And so shows that where your chloride is high, you have done more repair. For example, repaired area for 0.56 probability is 2,100, 0.35, 1,900, and so on and so forth, and you can fit a curve to this. So this is one case. Another case, 2019. This was also 2018, I think, 2018 or something like that. 2018 or something like that. Then 2019, 7 to 8 years internal chloride depassivation, groundwater seepage in the basement, because we couldn't do the detailed analysis there, but it is there all over the place actually. So total chloride was measured. We didn't measure, they were already there, the data was given. Carbonation was measured, 4 number. Out of 13, 4 were carbonated. 12 samples, free chloride was measured, and mean free chloride was 0.039, total chloride, so standard deviation 0.35, etc., and so on. Then this is another case where 2022, and you can see the crack, corrosion, river corrosion cracks. There also we went after 7, 8 years it showed corrosion. So already repairs were done, many things were done. And then we looked into the chloride, and 7, 8 years, carbonation would take much longer time. Because I'll tell you why. Because in Indian scenario, exposed concrete, carbonation doesn't occur so easily. The moisture, humidity condition required is 50 to 70%, or maybe 55 to 65%. So if it is 5, 7 say, VRC salt internal chloride, many of them apparently the court has asked demolition of some certain buildings with high chloride, and they are within very. In this case, the special case why I'm mentioning it came from plaster and mortar, right? Because chloride profiling was done by one of my friends. I didn't suggest because I could never imagine something can come from plaster. So I was thinking that it must be internal chloride, and random chloride measurements were done, and it showed there is a high chloride. Interestingly, 2 labs showed very different chloride before we took over. One showed the ratio of the chloride shown, acid soluble chloride shown by 2 labs, where 1:3. So one has to be very cautious about chloride testing. Sampling is very important. Powder, dissolving solution, IS that 13 something that is a long number is there. That's a good code, or a STM code, any code you use, but preparation of the sample should be. And titration should be done by, in my opinion, by electrochemical titration, Carl Fisher technique. Today they have automatic titrator, which does it automatically, but sample preparation is important. We find that in kitchen slab, this chloride at the surface is more, inside is less. And this is column. There also somewhere at the surface of the column is high. Now, chloride cannot come from curing water, because diffusion of water takes very long time. Diffusion coefficient is 10 to the minus 12 multiplied by something. It will take longer period of time. Even vapor has to go to a conducive condition for chloride, take the chloride along with it, because that will take place by what is called advection process. Liquid in solution form it has to go. That will take very long time. So I thought it must be from the tiles, and they said then we have a mortar between the tiles. And when you measured onto the tiles, right, measured onto the tiles had pretty high chloride. Not tiles, the mortar between the tiles and that. And even the plaster. So they use some contaminated water, sand in the plaster or mortar. And that's what it is. And 6 data in this case, there are many more. I'm not going to show all of them because then it will become a case. I don't want to do that. Now then we did something ourselves, we are doing through a project, and it's unfortunate my friend who was doing it, my MTech student, he passed away in COVID, but he gave me some very good results, some insight. We would have done more, but once one of my presentations somewhere in ICI, I just dedicated it to him. These are actually his credit. He did very good job. 2, 3 buildings. Some buildings were there. He chose 3 buildings, and they were 813 and 997 meters from the sea coast, because I thought, and also looked at the orientation and all that. And this was the kind of corrosion that we observed. And we selected surfaces which are along in the direction of sea wind, sea direction, opposite to sea direction, back face, and so on. We took sample from there, right? So orientation 45 degrees, etc., etc. We took samples from there, many samples. But I was expecting that it will give me a profile like what I got in the earlier case I showed. High at the surface, less at the inside. Sorry, it was not like this. You can see that these are the profile of acid soluble chloride. This is the profile of water soluble chloride. And this is the threshold. And chloride profile at 2.5 meter height, 3.2 meter height. None of this actually showed high chloride at the surface. Some showed almost equal at some height. And this showed that possibly it is coming from outside. One thing might happen, that wind blowing, but apparently this, when we looked at all the data, it was not telling me that it was all from external source. Then I should have got high along the seaside, less along the opposite side. It didn't happen that way. And they were within 1 kilometer of the seashore. Some cases I did find chloride at the surface is more compared to the thing, but not all cases, So I just picked up some showing that. So even people might be using wrong ingredients, maybe sand or whatever it is. Even in sea coast, one has to be careful. At different height we did, but face-wise we couldn't find any distinction really. Well, we would have done more analysis, but that's it. So in summary, all by few cases of internal chloride induced river corrosion. Carbonation induced is also there. But hardly any other sulfate I came across. I can consider my samples as a random samples for buildings because I have not seen situations such as in higher Himalayas areas where freeze thaw can be a problem. Dams are the ones where alkali aggregate reactions is a problem. This is not there. Because largely from buildings, and buildings are facing a lot of problem, not only in NCR or North India. My data is from NCR, Central India, Punjab, or Punjab, Haryana, Chandigarh, even Haryana, and there are data from eastern part of the country, southern part of the country, and so on and so forth. So this seems to be a major problem we get to look into. This is not a problem which Western world faces. Their code will not tell about all these things. Because their problem face corrosion problem because of de-icing salts in the northern latitudes, Europe and northern part of America. Bridges, flyovers, they do huge maintenance because of de-icing salts. All solutions. In fact, that is why they are trying to use a polymer reinforcement, rebars. But then there are problems with this, pultruded polymer composite rebars because of steel is still the best. I'll not go into that anyway, but still the best. Okay, so they have spent a lot of money on maintenance. Quality is major issue. Use of ingredients, groundwater without ascertaining their chloride is a big problem. Low cover depths, leakages and accumulation of water, poor drainage and detailing. Groundwater leakage in basement, that has to be seen. Detailing, waterproofing. You miss it and you are in problem. So major problems in building in India are early corrosion. Late carbonation will also take over after some time. But it would take a long time. Generally in northern India, it should happen much less. Free or total chloride samples from crushed cubes shall be made. Well, this is my opinion. It may be accepted or may not be accepted periodically. Mandatory, but periodically, not every time. You get a new source, a new source of material. You test for, if the concrete cube you have already crushed, you can have a simple automatic titrator in the lab, a grinding machine, powdering machine for concrete sample, dissolve it in distilled water, put it half an hour hot and so on, boiling water and so on, or put it in concentrated nitric acid, but pure, even water soluble chloride would do a good job. And that's what is responsible for corrosion. That should be a part if we want to avoid this problem. Yeah, carbonation-induced corrosion, not carbon. Carbonation-induced corrosion appeared late, some cases around 50 years. So what is way forward? I don't know how much time I had, but I think I'm...
Please continue for another 5-10 minutes.
Maybe 15 minutes. Okay.
Please continue.
Yeah. So, this basically durability means it should maintain its performance. And performances are fulfillment of function. Serviceability limit. Performance varies with time and gradual decrease of performance. Strength doesn't deteriorate. People, they say corrosion, do all kind of ultrasonic pulse velocity, rebound MR, and then test and even structural analysis. Well, that you can do independently. For other reasons, if you suspect there's a problem with the load carrying capacity. But if that is not the suspect, then corrosion problem is related to, it's something like, if I'm a strong person, even I can be attacked by a virus. So it's virus attack or something of that kind, bacteria attack, right? And generally, if you give energy to a material to produce, it will have a tendency, its potential energy will increase thermodynamically and its chemical potential high. So it will have a tendency to come down, but rate can be controlled, what we call kinetics can be controlled. So kinetics will be controlled. If you keep concrete for normal concrete for about 2,000 years, it will calcium, silicate hydrates, all will turn to calcium carbonate finally from where it has come, like anything else in the nature. So they deteriorate. As long as it is not affecting your performance, you are fine. But it can affect your performance. For example, you can see cracks, serviceability limit might be reached. So that's what it is. So concrete is not maintenance free, produces the expense of energy. Degradation specific is the service life. So durability is quantified through service life. Right? It is quantified through service life. And you repair normally accepted level, start repairing. I think this is from, I'm not sure, this is from book by Geoff May or, it's from Campbell Allen and Thorney, one of these books. But the idea might be even from CIB, which is now part of FIB. Yesterday they had that cartoon reserve thing. So it would deteriorate, and if it deteriorates, then you repair. Service life is, T ideal is the intended design life, for which you design the return period of wind, return period of earthquake. That's intended design life. There are other life like functional life. If the cinema hall has changed to shopping mall, that's functional life. Economic life when maintenance cost is too high. So that's what it is for the function, which might include other functional architectural issues also. So ideal service life would be maintenance free. TS service life, TSL I'm calling service life, is equal to intended design life. So if it is something like that, it would be ideal. You won't have repair and disruption cost. See the serviceability failure of RCC structure. If I look at it, the corrosion of steel occurs only 60 to 90% relative humidity. Carbonation occurs from 50 to 70% relative humidity, because you need carbon dioxide also air. And in case of corrosion, you need oxygen also. And chloride transport also occurs through water. So therefore it is actually, if you expose concrete all the time, it's not susceptible under deterioration. It's only during conducive moisture condition, that is relative humidity 60 to 90%, exposed concrete, which is exposed to air or wherever it is. Then only carbonation would occur, say 50 to 70% relative humidity in the cover zone. And every year it might periodically show up. This year, monsoon has come. During that period, you had high, it has become saturated, then dried, etc., etc. So wetting, drying is a phenomenon. Right? They include moisture, they need moisture. So annual cycle, and next year also it will be like this. Only small portion is shown here. In this one is a degradation period. Rest of the period, if it is more than saturated, say more than 70% relative humidity, carbonation will occur. More than 90% relative humidity, corrosion will not occur, and so on. So every cycle and every year, it is periodic. It is not continuous. And we must understand this. Therefore, it is better to consider climatic zone. And this is, I have presented in my IABSE paper. Of course, there are not many audience, as it happens in conference, sustainability related and linked to durability. So this paper is there in IABSE conference document, where I have presented this. I have presented this in NCCBM conference long back. Several conferences I have actually presented. And obviously, I didn't want to put it in a journal because it's India specific. So I set it to some foreign journal. Those fellows will not even understand or will not bother. They are not. Whatever, all said and done, we are in the global south, right? So the global north, well, they see us that way only, all said and done. So climatic variation consideration is important. And this climatic zone of India, and you can see that red one is what we call hot, dry desert climate. The dark yellow is warm, humid climate, where humidity is high, rainfall is high. Conducive condition will be for longer period of time. Dark yellow is composite monsoon, Delhi, and so on. And other one is cold. There are some moderate temperate zone also. And if you see precipitation zone, you can combine them and they do match, because precipitation controls the climate also. So corrosion zones, this is what I proposed. And this is what it is. Two types of zones, non-marine and then marine zones. Marine zone is the black one. So non-marine zone dry, non-marine zone warm humid, non-marine zone monsoon, and very high precipitation zone, some are there where possibly deterioration will be much less, because if it is all the time saturated, deterioration could be less. So that's what it is. So classification, this is I have proposed. And I so happy to see the draft. By chance, somebody has, which was not supposed to be circulated, the draft IS code, which has been circulated, not being circulated, but somehow or other I could lay a hand onto it. It did take some ideas from there. I think this should be fully taken and looked into it really. Everybody should look into it, all concerned people, because our condition, neither North America is going to do, not Europe is going to do. Copying from British code or international code is not going to help here. You got to look into your own, India specific. Research should be also Indian possibly. Okay, these are the equations for wetting and drying, where one of my students has worked, Professor Kaustubh Sarkar at IIT Mandi. He did work, did all kind of modeling, and because analytical capability, not everybody comes to me with analytical capability. Earthquake engineering, everybody will come with analytical capability, not me. But he was one, and my idea he could translate. And there is the second one. I'm proud of these guys, many of my research scholars who did work, starting from Professor Samsad Ahmad, who is now professor and possibly holding a good position and did very good research in King Fahd University. So this is modeling boundary condition. I think I'll avoid because I don't have much time. This is one gray area, diffusion coefficient, hydraulic diffusivity or diffusion coefficient. It needs lots of work, and we could find out moisture distribution, 0.6 water cement ratio from surface and so on. If somebody has question, I'll give it. This is Kelvin's equation can be used, and something more can be done, and you can find out cover depth for versus number of conducive days for corrosion or carbonation, etc., etc. And this is related to life cycle carbon also. Sustainability I have not covered there as much, but life cycle carbon days can be related. Carbon emission, this can be related, because more repair you do, more is the life cycle carbon you are giving, because you'll be using cement, etc., as the material. Sorry, going other way around. This is what we have produced. He produced rather. I was only the supervisor telling him what to do. So did a good job. So for various stations in India, choosing the climatic zone, Jodhpur for dry, Madras they call it because we got the data from this one, the IMD, meteorological, and they still call that station Madras. So put it, actually it's currently we call it Chennai. For all this, we could find out the conducive days for 60% relative humidity, etc., etc. And Kodai Canal, because where precipitation is very high. New Delhi, composite monsoon climate, and so on. Another student, Padala Suresh, is faculty professor at IIT Bhubaneswar. So he did work on the corrosion of marine environment. Again, the second topper of IIT Delhi, BTech. I was fortunate, I consider myself to be pretty proud that working with materials and somebody of that, high BTech thing, I could make him interested because I taught him materials course in second year BTech. So 2 tides are there, spring tide and, 15 days tide, diurnal daily tide, and 15 days, spring tide. They're there. You combine them, and wetting and drying, you model them and see that how chloride actually goes, right? So this is what it is, superimposed wave, first wave thing he did. Then he did this is for rain, which Kaustubh did, but I thought boundary condition I did, wind-induced one. Yeah, the mathematics I'm not going to show much anyway, don't have time. And this is the corrosion model, corrosion cracking model and all that. We did propagation time a little bit, and that I'll come to later on. So he took 6 stations in India, Vizag, then Marmagao, Mumbai, Port Blair, and Chennai, and then try to find out what is the lower limit of chloride threshold, because people have used different chloride threshold level, mean chloride threshold level, because this is the whole problem. This is still a gray area, and green is the lowest chloride threshold, highest upper limit of chloride threshold. So mean, and corresponding to this, what is the cover depth you require for all these cases? You could find out for 100 years life, 75 years of life, and so on by modeling. This theoretical model, 25, 50, 75, 100, what is the cover you need? That's what was estimated. But this is not this is only theoretical estimation. Validating is not very easy in any one of these cases, and that's what it is. So, as I said, this is so thus guidelines for subtropical latitude, North America or Europe may not be directly applicable to the tropical Indian condition. I would like to highlight this. And copying something from abroad and doing it, I don't think, structural failure doesn't occur here. Rarely structural failure occurs because it gives you so much of signal. If structural failure, you leave it to the structural failure level, except for pitting corrosion in pre-stressed concrete where no signals are given much, and pre-stressed where one of them snaps, it can have cascading effect. Many of them bridges, actually some of the bridges have shown this kind of failure, actually, because they didn't know even what is happening. So one has to be cautious. So these are the sites, that is what it is, and this is already I've shown, I'm not going back there. Durability, of course, quality of concrete cover, elastic modulus, tensile strength is important because fracture depends upon tensile strength and elastic modulus. Blended cement does improve. Corrosion resistant rebar can help. And this is the modeling that we did. One of my students, he's again from IIT Bombay topper, IIT Bombay BTech MTech combined topper, Kamal Jain. He did this numerical analysis, fracture of corrosion. But unfortunately, there's no lab data to verify this. So I'm going through fast because this is numerical modeling. So basically, Faraday's law comes into picture. Corrosion rate is the current and from that, using Faraday's law, you can find out how much rust will be produced, how much pressure it will produce, depending upon whether it's a constant rate or you use a low varying rate, etc., etc. Different conditions are there. I don't think uniform pressure or uniform displacement approach, and it's a mechanics problem straight away. These are the ones which have been used, corrosion inhibitors for protection. Cathodic protection is also being used in marine structures, where very important. If you know the place where you want to apply this, it's fine. But it's a very wide place, there is a problem. Corrosion inhibitors, now even there are migratory inhibitors. We have done some work onto that. I didn't put it here because it has already becoming too long. So there monoethanolamine, ethanolamine, etc. Of many of our friends have in India, they are actually supplying this. Krishna Conchem, Fosroc, they are supplying this. But their performance need to be validated inside lab. They have performed well. Some of them are very good for chloride. Galvanized steel, their performance has been told pretty good. So apparently it delays. Even the threshold chloride tends to be more. Galvanized rebar, corrosion initiation, because it's already there is a zinc coating which will first get dissolved and then actual steel bar would be affected. So that's what it is. Epoxy coated bar comparison is there, but they have some reservation about them by some people. In fact, it is said Florida Key Bridge, which used this, also still failed in US. So for steel, this is a formula. Stainless steel compared to ordinary steel. So there are details available. So this is that same epoxy thing. But stainless steel, they've seen, Japanese have done quite a bit of work on those. Type 316 bar with chromium and nickel and molybdenum. They are the ones. Molybdenum even improves fire rating and fire resistance and all. So cost increases, durability also increases. You'll have to see that. Now, there's something called pitting index in case of pitting corrosion for rebar or steel. And they have A, B, C, D grades. For A, pitting index is 38, which is very good. E, pitting index is 11. For structural durability, C, D, E are good enough. That's what the Japanese say. And their mechanical properties are also given. It's all available. Okay, I'm gradually coming to, this is cathodic protection. We did work in 97, 98 in lab scale on this. And there's a paper in Indian Concrete Journal, 98. Basab Raja, Shamshad, and Basab Raja was the MTech student who did the work. Shamshad wrote the paper, I was a guide. And this is the circuit, equivalent circuit. This is available. And we put in a sacrificial anode. But then one gray area was the I required. How much is the current? So how much you find out how much area of sacrificial anode you need to depend on the current. This is a really gray area. And you could calculate using Faraday's law. I'm not going into that, but that's what I say. I record is a problem. Inside, how do I determine this in buildings? And when there are chloride, internal chloride all over the place, if I miss a place, it will be there. Sometimes system do not work. Monitoring is minimal place because sacrificial anode will get consumed. So markets, it's a marketing is going on, but I'm not very sure about the performance. In fact, my experience is that somewhere it has not worked well. But at the same time, I would like to see that it has worked well over a long period of time. The gentlemen from abroad who interacted, or one or two gentlemen who interacted with me, they claim so many things, but I'm not sure. It can be used for oil rigs, which has been used long back. Peter Puller's tracker, I think, or Padmanabhan book gives you the details of that. But that's very localized. Single pier or column you can't use because the area is not large. In a building, there are so many columns. From where water will come, you don't know. Today, if it is internal chloride, tomorrow water might come and it's a problem. So you have to see that water is out. That's more important. And this, they relate I required to total chloride content or acid soluble chloride content based on a 1986 conference paper. I really do not agree. It's a challenge. Well, water treatment, surface treatment, coating, polyester, your polyurethane foam. If there is moisture, they do very good job. Epoxies, acrylics, and so on. There are coatings, hydrophobic lining like silicone, pore blockers. Even polyurethane foam might block if it gets water, and then surface rendering and all that. And, the chemistry I'm not going into. So these are waterproofing treatment. They do a good job. Coating, surface treatment, coating of rebar, corrosion inhibitors, cathodic protection. Now, let me talk about a little bit, last 2-3 slides, finish it off. If you do a repair, should do a repair so that it goes up to the end to intended design line. And best is, of course. And I've already said that exposure and service life degradation period is small. So we have to know that. Cracked concrete doesn't prove much of a problem unless otherwise the concrete is bad. It's isolated one crack or maybe two cracks. Corrosion may not occur because the cathode will not transport water, FeOH, etc., etc. Electrolytic situation in cathode area will be low. This has been shown by BB doing an experiment in laboratory in 1990s or 80s. BB came in Institution of Engineers Journal from England. This is the repair process. I don't think I'll go into this. Remove concrete up to some millimeter, at least what it says, the finger should go below the rebar, clean it up, and cut it. Nobody is doing cutting in India in this type. What they're doing is hammering and taking, because our manual labor is cheap, but that's not the best way to do. Actually, it should be cut, exposed, and putting a bonding coat and then repair with a polymer modified. The cost is important. Life cycle cost, initial cost is CI. Repair, if you are doing more number of times, obviously your cost is important. And inspection, if you do repair, will reduce. Maintenance cost and probability of failure in an extreme case, how much will be if there is a failure of an element, that probability could be low if you are doing regular repair. But in bridges, it can be still higher, as I said, because you may not be knowing if you miss out that point where pitting is occurring. So repair cost, etc., etc. This is kind of a model. You improve the specification, initial cost is high, but maintenance cost will be low. Well, FCIB, Comite International de Béton, I think is part of FIB. I'm not sure the French acronym. Perhaps this was there earlier. They said there are two units which join together to become the FIB. So major factors they consider is quality, environmental condition, and loading condition. Right? And exposure condition is again environmental and loading. So this is aggressive, non-aggressive doesn't, is work here, not the IS 456 type. They suggest the inspection frequency based on that. Static or fatigue loading. For example, both environmental condition and loading should be taken. Very severe, aggressive environment with cyclic loading, severe with aggressive environment with static loading, or non-aggressive environment with cyclic loading, and non-aggressive environment with static loading. Importance of structure you should consider. If there is already, chloride is inside, I think your maintenance becomes very important. Inspection becomes very important. And these are guidelines they have given for inspection cycle. This is not structural audit, sorry. I mean, somewhere apparently in the code says that you should have a 5-year structural audit. I'm not sure why. I have not understood. Right? Does the structure deteriorate? I mean, the strength reduces, loading capacity decreases, not because of this kind of virus attack or bacteria attack. I'm not very sure. And they try to combine both of this together, failure with unless you have attended it. And pitting corrosion in case of pre-stressed concrete, failure has been very rare. If you look at failures, people have not attended them. Even other day I saw in iStructy thing, there are, spalling off of mortar in that building which has been asked to be demolished. Now people are still staying there without maintaining, without repairing. Well, I don't believe normally in God, but here I have to say that God saved them. There's another case of collapse in Gurgaon, one tower. Somebody, the fatality was there. But then they were repairing without, the bars were not proper apparently. And they were repairing them without any problem. The floor had to collapse. Excess load of repair also would have come. So this should be seen separately than the structural problem. A structural audit will not save this problem. Sorry. You have to look into inspection. They are saying 2 types, routine and extended. Now, routine means visual inspection. Do you see a corrosion cracks? Do you see moisture marks? Extended means instrumental. If you see them, would you do Hubsel potential to see the possibility of corrosion, or take sample and see? First time if you see, you might also do chloride, see carbonation, but basically that sort of thing should be done every 6 yearly if it is class 2 type of structures. If there's already there has been a problem, I'm sure you should take it as class 2. This is FIB guideline, if I may say so. They have a code I could see yesterday on durability issues. I hope they maintain similar sort of guidelines for inspection and things like that. But you can model it and find out the cost. As I said, because cost of repair will increase. When condition of structure will deteriorate further if you don't do it. So you can model it. So time of repair can be taken as T/2, inspection time if it is T, average time you can take. And you can simple model you can do. Continuous monitoring is T equals to 0. That can be done in a marine structure. You can have instrumentation today. Even cloud you can put in the IoT can be used. I'm not sure about the instruments, their reliability, but at least they can give, some of them can give good indication. Supposing you embed a corrosion current density, corrosion current density meter inside, which in Singapore they have done. That's what Professor Basir was presenting in one of the lectures. Singapore, I think Singapore only, somewhere in the sea. Well, cost involved is there. So it's a special case. And cost will increase. Inspection cost will increase if you increase the frequency. Repair cost and disruption cost will reduce, because disruption is also a cost, and total cost will be minimum somewhere. So that's what it is. And you can actually, time of inspection, you can model it with, provided you know the inspection cost per survey, expected repair cycle time, and increase in repair cost for a delay of 1 year, etc., etc. And this model I am repeating again. So one can even calculate out, but this will be somewhat getting the data, if not a PhD, a master's problem. But then that's not my cup of tea anymore. I've finished that kind of job. Thank you very much. And if you have any questions, I'll love to give you answers.
Professor Bhattacharya, excellent presentation, because these things are not available in the books. And the consultant sitting in the office doing some design thing, they say the design life of structure is 100 years. But what is happening at site? The things are different. So my question to you, Professor Bhattacharya, first, before I allow the other. See, once the concrete is alkaline, pH value 13 plus, then, whatever is the service life, there cannot be any corrosion. there cannot be deep activation and corrosion. How we can ensure this alkaline effect may not go down? I mean, is
No.
there anything? I mean, you can just suggest.
No,
If we want real
basically,
life,
yeah.
I mean, we need to see, of course, relative humidity, you said, should be controlled. Temperature should be controlled. Different climates, different conditions, marine, non-marine. But the main thing I could see, the concrete can remain alkaline. Then probably, I mean, things corrosion may not occur.
No,
What is your comment on this?
no. Problem is not alkalinity. Problem, even alkalinity will reduce only in presence of moisture. Relative humidity 50 to 60%.
Mm-hmm.
See, you are not going to remove carbon dioxide from the atmosphere. Well, it's over
Yes,
other way
that's
around. It is too much of a
That's
problem at the higher atmosphere level, right?
Right.
At the upper atmosphere level. Now, the
Mhm.
carbon dioxide is there. Only thing you can suffocate it or make it thirsty by
Mhm.
keeping the water away.
Mhm.
Now, that means that it has to be impervious at the cover level.
Mhm.
Now, the cost of keeping it impervious will have to be seen.
Mhm.
The coating that has been going as anti-carbonation coating, they're not anti-carbonation coating. Let me put it.
Mm.
Somebody should do, one of those salesmen should come and challenge me. I love
Mhm.
it. They're actually waterproofing compound,
Mhm.
waterproofing coating. And if it is done all over the country, that's also not good.
Mhm.
So what you got to do is you choose the right kind of, if we can do that modeling that I was talking about, there are a lot of gray area. And unfortunately, no structural engineer or a designer, or even if you have a material specialist in the system, will use it unless you have a software for the same thing.
Mhm.
That's a large project. We have so many software specialists all over the world, but we don't have a single, very few Indian software in the scenario.
Mhm.
One or two I have heard about, but I have not heard about most of them. So it is
Mhm.
software, if is developed, then it is possible, and material properties. So for example, for water cement ratio 0.4 or 0.6, with a given type of cement,
Mhm.
how many years it will sustain for carbonation depth to go up to the cover depth?
Mhm.
That we can find out. But you cannot stop alkalinity to go down if the moisture condition is conducive for carbonic acid to form.
Right.
H2CO3, H2CO3 formation, CO2 plus water. This you can't stop. As I said, the kinetics
Yes,
you can stop.
we cannot sustain that alkalinity.
Yeah. So
Due to
potentially you
carbonation.
can, alkaline materials are not stable.
Mhm.
They'll be attacked by acid.
Mhm.
If your pH is 7, then it is stable. But at
Mhm.
pH 7, steel is not stable.
Yes.
So all sorts of, this kind of things are there. We have a man-made material. We have to understand that and do it accordingly.
Mhm. Then, sir, second question, see now climate change, global warming. I mean, we have got computer software monitoring, but its gradual effect on the structure, would remain. I mean, what is your, direction to the youngsters?
No, the climate change is not going to directly affect your structure as such. I mean, it can cause disaster.
Mhm.
So climate change, simultaneously, you are talking in terms of disaster resilient structure.
Yes, disasters
Climate
are
resilient, disaster resilient structure. So climate change as such, supposing the tidal wave becomes higher, splash zone,
Yes.
there it can have some sort of effect.
Mhm.
A structure which was not in marine zone now becomes in marine zone because seawater level has risen.
Mhm.
That can be a problem. So climate change, it can have a secondary effect, not direct effect, because it will cause something and that will have an effect. Carbon dioxide at the atmospheric level is not so high. Upper atmosphere it is high. That's why it is greenhouse gas effect is coming. Greenhouse effect is coming. That the terrestrial radiation is not able to go up.
Mhm.
The temperature rise is occurring. So that is the scenario.
Mhm.
I just want to point out that 100 years of life of concrete structure is not there. Anybody says is wrong. After 100 years, a concrete structure will not die down. It is contextual. Life of an inanimate subject is contextual. You talk in terms of intended design life. An atomic reactor structure, I'm sure my structural friend will agree, they take such kind of importance factor that intended design life is 1,000 years. Because catastrophe it can cause, it's notional. Wind load you take for 100 years, 50 years wind load for normal building. So intended design life is 50 years. Right? Because you don't know, you cannot block the money of current generation for future generation. They might do something, they will change, the whole system might change. So therefore, that's another side of it also. So life is contextual, intended design life, functional life, economic life, etc. we talk of. And building may be in service for 50 years or maybe for more if I maintain it well.
Vikas, say the other question if we have.
Yes, sir, there are a few questions. First,
Please.
Mr. Arnab Ghosh asked, I have seen extensive distress related to corrosion of rebar in the slabs over which big central AC units are placed. Which is the main cause of this?
No, the water is coming, na? Central unit AC, the moisture would be coming.
Yes, sir. Yes, sir. Yes, sir.
Moisture, you see, the water is the main, moisture is the main thing. If you have a conducive relative humidity condition, not saturated, not dry, but relative condition, then that's why, that's actually not only that, your split AC, the outside unit, where water falls, if it is not straight away going to the ground, the corrosion is occurring.
Yes, sir. Thank you, sir. Mr. Gangarpal Singh asked, what is the permissible limit of free chloride and total chloride in concrete or mortar?
As I said that this is actually, I have shown you a graph which shows that, no, mortar is not a problem, but mortar added to the concrete RCC is a problem. So, right, mortar itself is not a problem, but mortar added to RCC is a problem. Now, I am just going to one of the slides where I've shown you something. You see, the people are confused about it. We are not very sure because codes became stringent when we looked from code up to 2007 or 8. They became stringent and stringent. Earlier, they were allowing higher chloride. Later ages, they started allowing lesser chloride. I'm just coming to that one slide. I think I have come very close. Yeah, here you are. You see, there are 3 levels of chloride we are talking of. Chloride threshold level. One is a chloride threshold level for upper chloride threshold level. The minimum chloride, see, this is the chloride threshold level, depth. So upper chloride threshold level is much higher. And lower chloride threshold level is much less. Now, this is 0.025 is what I have been, on an average, I have been using, because 0.15 have been suggested by, or maybe some literature. I don't think I am using. Some literature, Visara, for example, in his paper in 1980s, in ACI, American Concrete Research, 0.15. If I take that 0.4% by mass of cement, it works out to be around 0.034 or 35. So we'd say that perhaps we are quite confused. As you can see, there is a difference, significant difference. The covered chloride threshold depth, very high if you take the lower chloride threshold limit. And if you take upper, then it's very, the depth is very, very low. I mean, lower and upper. Sorry, this is chloride threshold depth. Right, straight away you will get 50, 30, 20 mm or 10 mm or so. So at 10 mm it reaches and it will carry on actually. No, I'm not sure. I think it's underground. It should be. Lower chloride threshold depth should be this. Lower chloride threshold depth, threshold if you have. So the depth is 200. Yeah, lower threshold chloride reaches much inside. Upper chloride threshold right in the surface. So that's over the any duration, number of years. Let's say you take 20 years, upper threshold chloride quickly reaches to 20 mm. 20 years, it reaches to a value. So 50 mm thickness. Right? 50 mm thickness, Upper chloride threshold is already reached. And this is the mean. So there is a problem, and that's still, I think it needs to be looked into. But people who do work safe, you take 0.025 or 0.0115 for existing structure. I'm not talking of the fresh concrete. That's code is given, and that's a good enough. 0.6 kg and 0.4 kg, etc. These are fine.
Thank you, sir. Thank you. So, Mr. Chalari Suresh asked, in areas with a moderate climate, how does the lower relative humidity below 75% impact the carbonation rate compared to regions with higher humidity levels?
No. There's nothing like higher humidity level or lower humidity level. Let's understand this. You see, you'll not have throughout the year same humidity. So I'll go to that regions. I'll resolve the region part of it. Then we'll talk about something more. Yes, this diagram is good enough. Now, even previous diagram will be better. Previous diagram will be better. Yes. So you see, you have, what you are saying is higher humidity region like warm and humid climate, where relative humidity is above 55%, right? And the precipitation is I'm not able to see because my photograph is coming here. Precipitation monthly below 5, the number of clear days 20, and this is below 20 days monthly, and more than 6 months you'll have this kind of weather. So if you are below 75, moderate, actually I have not taken Bengaluru for example. It's a moderate climate. It will have much less number of conducive day for carbonation, right? Below 75, depending upon the situation, because this is almost same. Well, I have not really taken this. I didn't take Bengaluru as one of them, but 75 below means what? If it is 70, carbonation will not occur, right? This is the climatic classification done for building engineering. What you call air conditioning and things like that, related to energy efficiency and so on. So climate specific building design, functional design of building. So below 75, if it is something like 70, well, no carbonation. But if it is between 55 to 60, so some month it will be below 75, 4 months it may not be, but temperature range is 25 to 30, that doesn't make much of a difference. Precipitation still is low. So that's what it is. Here above 5. They are actually conducive day for carbonation, may be somewhat more, because 55 to 60% humidity it may last every day. I mean, during the monsoon season, it will be saturated. But after monsoon, for many days, it will be there. So it has to be looked into. 50 to 70, you can say the carbonation occurs. We have not calculated for this, for moderate. We calculated for hot and dry, warm and humid, composite. That's the main 3 climate. Then we did for another one was for this one, Kodaikanal, which has a high rainfall, very high rainfall, high precipitation zone, very high precipitation zone. There practically it was pretty safe in the sense that most of the time it's saturated. So I think it was because the rainfall data that was available to us, we used that. I suppose, Jodhpur, but Chennai, Bangalore, Kodaikanal and New Delhi. So this is desert. Chennai is warm humid. Bangalore we have done, yes. So Bangalore, but also this is only a simple calculation. Assuming 40 degrees centigrade, 60% relative humidity, or 20 degrees centigrade, 60% relative humidity. If it is constant, it needs more modeling. So it says that conducive day for corrosion in Bangalore is 117 days, 113 days, 117 days, 215 for a water cement ratio of 0.4, where Jodhpur will have none. No days. If you use 0.4, no corrosion will occur in Jodhpur. If you use in Madras, Chennai, more. So I think that answers your question somewhat, but we have made so many assumptions. The temperature is 40 degree. Bangalore will not have 40 degree centigrade temperature unless it's exposed. It will be 20 degree centigrade Celsius. So then you have got this, and this is comparable. This is almost comparable, right?
Yeah.
0.6, 0.4 is somewhere here. Yeah. So this is the kind of thing. But
Yes.
one can calculate out. This is theoretical calculation.
Okay.
Value of the hydraulic diffusivity is to be looked into.
Yes, sir. Thank you, sir. Thank you.
More research is required in this. And those who are research scholars, I'd suggest that you get into this India-specific research. This is India-specific. No code will give you. Americans will not do it because it doesn't matter for them. They will have, although southern part of United States has got a desert area, but I don't think they are similar to Indian scenario because we have Himalayas which does something different, right? And monsoon is India-specific. Okay.
Yes, sir. There is another question from Mr. Venkata Gavaraju. Is there any guideline for reliability analysis for concrete in any code to estimate the life after deterioration?
No, why should I be doing it reliability? I think it's ridiculous to do reliability analysis here. Will I allow it to fail? You are talking of structural collapse. No. Limit
Yes,
state of collapse will not be reached at all. Why should it reach? I'll repair it.
correct.
Why should I do it? This is a fancy thing because reliability is a complex statistical and mathematical tool. So if you are mathematically, you want to show that mathematically you are great. I personally think this is useless. There are many research in the world it is going on. But why should it? If it is get unattended, right, then particularly bridges, this can happen unattended if it goes. But other deterioration, how much deterioration? Single bar, for example, in reinforced concrete, there's so much of redundancy. One bar lose say 50 to 20% of its diameter, 30% of its diameter. Is the structure going to collapse?
No.
The column sizes are done to save shuttering cost. You group them. So for buildings, surely this is not applicable. In Indian scenario, I do not agree with that. I'll do repair before that. Reliability is not required. For reliability, you got to know the probabilities. And probabilities are totally unknown in this kind of scenario. Unless you have got you can use Markov's chain. I have actually done something along that line sometime in master's project. Because if you know today how many of them are above threshold chloride, out of total you have, so probability of depassivation, if you know, it can remain in that state or go to another state. That probability you can find out if you have data next 5 years later. So Markovian process you can utilize, but this doesn't make much of a sense. Because in buildings, I should rather do maintenance, inspection to monitor it and do not allow it to go deteriorate further.
Thank you, sir. Thank you, sir. So this is the last question by Mr. Satyajit Das. Does RCPT test provides a clear picture of chloride effect?
No, it measures resistance. What gives you? It gives you charge, coulombs, under a potential gradient. So if your resistivity of the concrete is high, you will have much less coulomb. So
Yes.
if you put fly ash, if you put pozzolana of any form,
Yes, blended cement, you said.
yes, blend. So RCPT values will be, much better for you. Actually, resistance is a better tool. Rapid chloride test, people have tried to relate it to chloride ion diffusion coefficient. That's also not correct. In fact, we did a study on that in a master's project, part of a PhD project also. There are different methods for measuring chloride ion diffusion coefficient. And the RCPT has also been used. But remember, the phenomena is different. When you are applying an external potential, positive ion, anion, and cation move in different direction. In natural system, it doesn't occur that way. Diffusion of chloride, along with, but more problematic is the advection, going as solution. So I don't see RCPT, in my opinion, RCPT should not be a test used at all. Not in India, not anywhere. Aceto has been putting it, from there it came. So I
Thank-
suppose RCPT should not be used.
Yes, sir. Thank you, sir. Thank you. Yeah, Dhawan sir, these are the only questions.
Thank you, Professor Bhattacharya, for sparing your valuable time and sharing your lot of knowledge. The message through Bhattacharya is we have to do the right job at the first time, the right type of material, right type of workmanship, including the farm work. There is no shortcut. If we can do that, whatever do we do, so that will bring the durability part, and that's all. So thank you, Professor
Thank you very much.
Bhattacharya, once
Thank you,
again,
everybody.
for
Namaskar.
sharing your knowledge and experience.
Namaskar. Thank you.
So the next lecture again on 27th of March by renowned Professor J.L. Humar, who has been my senior colleague in CBOD. He is there in Canada since 1975. So he is one of the renowned structural engineers, not in the Canada, but all over the world. So do join that. And this is what I would say. So thank you once again. And let's now close the today's session.
Okay. Thank you.
Thank you.